All right. First of all, I am an old math teacher and I have to talk more about n choose r. First of all, there are multiple ways of writing it. This is the way that's in the videos, and that's what's on your calculator, so that's great. But the other two ways are also very common. When I used to teach this in data management, I would use all three interchangeably. Remember last week, we talked about tossing 5 coins, or a coin 5 times, and we're talking about a probability of exactly one head coming up. I wrote this. I wrote head and 4 tails, and then the head in the second spot, and so on. And that was really easy to do. However, at the time, I said if we changed it to exactly 2 heads, it becomes much more challenging because it could be head, head, tail, 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 head, tail, head, tail, tail, and so on. And we could have in the first and third, first and fourth, first and fifth, and then second and third, second and fourth, second and fifth, and then the third and the fourth, third and the fifth, and lastly the fourth and the fifth. Would actually be 10 of these, which is a lot of writing, especially for an old guy like me. And I said we would get to that later. By the way, each of those probabilities would be expressed as 1/2 the exponent 1 times 1/2 the exponent 4. And yes, you can rewrite that as 1/2 the exponent 5. But I want to point out that this first one represented the success, or getting the head, and these 4 represented the tail 4 times. But it could happen 5 ways. So the answer to that question, how many ways can a head appear exactly once, would be 5 times 1/2 the exponent 5. You could combine those. So let's change this now to a single die so that we have not 1/2 as each of the two probabilities. And we're going to say success is rolling a 1. So our probability of success will be 1/6, and of fail will be 5/6. And we're going to roll it 4 times. And I want the probability of exactly 2 ones. Well, like I did a minute ago with 5 coins, if I have 4 rolls, I can have success in the first 2, first and third, first and fourth. And I'm modeling systematic counting here. Or the second and third, second and fourth, or the third and fourth. So there are 6 ways of having the 2 successes be arranged among these 4 things. And that's where this concept of 4 choose 2 comes from. And 4 choose 2 is 6 because there are 6 ways of doing that. There are 6 ways of these 2 successes appearing in a group of 4. So the answer to this would be that right there, because no matter how they're arranged, the 1/6 appears twice, and the 5/6 also appears twice, and it happens 6 times. So this right here is the probability of that happening, okay, of a 1 coming up exactly twice. Now I want to go back and talk about a formula for this. Like, where are these numbers coming from mathematically? Is it just something magical? Did someone count all these things and then, enter in a calculator and save it? Well, no. The formula, n choose r, looks like this. An n factorial means n times n minus 1, n minus 2, and so on down to 1. Or 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So 8 choose 3, this right here, becomes 8 factorial over 3 factorial, 5 factorial. So if you didn't have that button on your calculator, you could still do it if you understood what factorials are. Notice if I did 8 choose 5, And my 8's getting a bit big there. Make sure that the numbers are subscript. Notice it's 8 factorial over 5 factorial, 3 factorial. Well, this is the same as that up there. The 3 and the 5 are reversed, but multiplication is the same when it's reversed, so they're the same thing. That's pretty important. Now, somewhere in your lives, whether it was in the back of your math class, maybe you've studied this, but this is called Pascal's triangle. You will notice that down the side, both sides are all 1s. You might also notice that this number there is the sum of the 2 above it. This number here is the sum of the 2 above it. This one here is the sum of the 2 above it. So you can actually build Pascal's triangle by starting off with 1s along the sides and building it. Remember we just did, a few minutes ago, 5, choose 1. That's that number right there. And I talked about the fact that I could have the numbers in the first and second. If I was choosing 2, I could have numbers in the first and second, first and third, first and fourth, first and fifth, second and third, and so on. And there were in fact 10 of them. So this here is actually 5, choose 2. This one here is 5, choose 3. So I could do the first, second, third, first, second, fourth, first, second, fifth, second, third, fourth, second, third, fifth, and then third, fourth, fifth. Bottom line is there would be 10 of those. And you know what? If I have a group of 5 people, if I pick 2 of them, I'm also not picking 3 of them. I could have just as easily not picked 3 picked 3 and left 2, which is why this and this are the same. You will notice this number here and this number here are the same. Going back to those two, this number here would be 3, choose 1. So there are 3 ways of choosing one person from a group of 3. I'm going to write down 3, choose 1. This one here is 3, choose 2. So, as I said a minute ago, if I'm choosing 2, I'm actually leaving 1. So 3, choose 2 is the same as 3, choose 1. That's why these tables are symmetrical. Something else to notice, if I look at the sum of this row, it's 8. This was 3, choose 1, right? And this here was 3, choose 0, which sounds silly, but you can have an empty set, a set with 1 item in it, sets with 2 items in it, and then the entire set. The bottom line is those are all the possible subsets of a set of 3 items. Another way to think about this is for each element in the set, it's either in or it's out. I have 2 choices for each of the 3 elements, and guess what? 2 choices 3 times is 8. This one here, this row, it adds up to 16. This would be having a set of 4 and choosing none of them. In other words, an empty set. There's only one way to do that. Choosing 1. There's 4 ways to choose 1 from a set of 4. Choosing 2. Well, we did that a few minutes ago with the rolling of the single die. Choosing 3, same as leaving 1. So there's 4 ways to leave 1 out of 4. And there's 1 way to take the whole set of 4. Whole set of 4. Each element in the set is either in or it's out. 2 choices. There are 4 of them, so I have to choose yes or no 4 times. All right? So this is my background to N choose R. And this table, this triangular set of numbers is called Pascal's triangle. And it basically is a list of N choose R's. And it goes on forever. And if you had to come up with those numbers without using your calculator, this is actually how you could do it.